Hello, class. Our next question on here, question number 3. This one has the following picture shows 2 railway cars, which did not get into my picture on here, but it shows 2 railway cars with a buffer spring. We want to investigate the transfer of momentum, that occurs after car 1 with initial velocity v sub 0 impacts car 2 at rest. This follows the system. The vector x double prime is equal to a matrix negative c sub 1, negative c sub 1, c sub 2, c sub 2 times the vector x, with c sub I being k divided by a mass m sub I, for every I being 1 and 2 in this case. We want to determine the eigenvalues and associated eigenvectors with the coefficient matrix A. So the determinant of A that we will get from this when we subtract lambda across that main diagonal, we are going to get negative c sub 1 minus lambda times c sub 2 minus lambda. We have negative c sub 1 times c sub 2. That will give us positive c sub 1 times c sub 2. And well, that gives us nicely negative c sub 1 times c sub 2 plus c sub 1 times lambda minus c sub 2 times lambda plus c sub 1 times c sub 2. And that factors nicely, well, I shouldn't say factors, and combines nicely to make c sub 1 times lambda minus c sub 2 times lambda. And we also have a lambda squared that I did not put into here. Let me quickly add that in very quickly. We have a plus a lambda squared here. And we still have plus c sub 1 times c sub 2. Okay. So that would then, after we cancel out our 2 terms on here that are the same, these two, but different sign, we get c sub 1 times lambda minus c sub 2 times lambda plus lambda squared. And we could factor out a lambda. So this would give us, I'll write it down here, lambda times c sub 1 minus c sub 2 plus lambda is equal to 0. So because of that, we have two solutions. We have lambda is 0, and the other one would be that lambda is equal to negative c sub 1 plus c sub 2 as our 2 solutions. So we have our 2 cases. Let's start with lambda is equal to 0. So subtracting 0 across our main diagonal will just give us that same matrix back. Negative c sub 1, negative c sub 1, c sub 2, and c sub 2. Times our eigenvector v sub 1 is supposed to be equal to the 0 vector. This will make negative c sub 1 times A minus c sub 1 times B is equal to 0. And c sub 2 times A plus c sub 2 times B is equal to 0. And well, the only way that we could have these two and get 0 back involving these is if we let A to be 1 and B to be negative 1. Likewise, for case number 2, this would be lambda is equal to negative c sub 1 plus c sub 2. We will get the following matrix when we subtract this eigenvalue across the main diagonal of negative c sub 2, negative c sub 1, c sub 2, c sub 1, times our eigenvector v sub 2 is equal to the 0 vector. Our 2 equations then are going to be negative c sub 2 times A minus c sub 1 times B is equal to 0. And c sub 2 times A plus c sub 1 times B is equal to 0. These don't particularly correct, right? If we factor a negative in this first equation, we get the same exact equation back. So the only way that these two here are both satisfied is if C sub 1, excuse me, that's not the way for me to say that. Only way that these two here make sense are if the values of A and B then, if they correspond then to each of these specific values. So if A was in this case C sub 1 and B was negative C sub 2, whatever those so happen to be. So based on our first, let me label these to make them make sense. For lambda sub 1 being 0, our associated eigenvector v sub 1 would just be the vector 1 and negative 1. Likewise, for lambda sub 2 being negative c sub 1 plus c sub 2, our associated eigenvector v sub 2 has to be c sub 1 and negative c sub 2. Thank you.